Welcome to the Q&A session 14 from the playlist of electromagnetic induction. The topic is the mutual inductance in a loop due to a long current carrying wire. And this session is in continuation of the session number 12. In the session number 12, we have studied about the mutual inductance between a pair of two coils. And based on this topic, I have selected one question for this session, and the question is: a long current carrying wire is placed near a square loop of side A at a distance x from it. Find the mutual inductance between the wire and the loop. So this is the figure which was provided along with this question, and in this figure, this is a long current carrying wire in which the current I is flowing, and this is a square loop of side A, and the side AD of this square loop is placed at a distance x from this current carrying wire. So the mutual inductance between the wire and the loop, that is M, this will be equal to the magnetic flux which is linked with the loop divided by the current which is flowing in the wire. So here we have to find the magnetic flux which is linked with this square loop due to the current which is flowing in this long wire. So the magnetic flux phi will be equal to BA cos theta, where A is the area of cross section and B is the intensity of the magnetic field due to this current carrying long wire. Now we know that the intensity of the magnetic field due to a long current carrying wire is equal to mu naught I upon 2 pi r, where r is the distance of that point from the current carrying wire. Now here in this case, we have to find the magnetic flux which is linked with this entire loop. So in this case, what we will do is, I will be considering one small element of thickness, say dr, and this element is situated at a distance r from this wire. So I will be first of all finding the magnetic flux which will be linked with this small element of thickness dr, and then we will integrate in order to find the magnetic flux through this square ABCD, I will integrate that value within the limits of x and x plus a. So the magnetic flux due to this element of thickness dr and which is situated at a distance of r from this current carrying wire, say dB, this is equal to mu naught I upon 2 pi r. Now the area of cross section of this element will be equal to, let us say it is area of cross section of this element of thickness dr. This will be equal to the length of it, which is equal to a, and the thickness of it, which is equal to dr. So the flux, say d phi, which is linked with this element of thickness dr, will be equal to mu naught I upon 2 pi r into area of cross section is equal to a into dr, and here the value of theta will be equal to 0. So cos theta will be equal to 1. So here theta is basically the angle between the direction of the magnetic field and the normal to the surface. So in this case, this theta is equal to 0, and since cos 0 is equal to 1, therefore the value of cos theta will be equal to 1. So d phi is equal to mu naught I upon 2 pi r into a into dr. Now, by integrating this equation, say this is the equation number 1. So, by integrating the equation number 1 within the limits of x and x plus a, because we have to find the magnetic flux which is linked with the square ABCD. So, the limits of integration will be from x to x plus a. So, d phi is equal to mu naught I upon 2 pi r into a into dr. So, by integrating this equation within the limits of x and x plus a, I will be getting the another equation, that is mu naught I upon 2 pi r into a into dr. So phi will be equal to, that is the magnetic flux which will be linked with this square loop ABCD will be equal to, now this integration can be written as mu naught I, a and 2 pi are constant, so that will be taken out. Mu naught I, a upon 2 pi is a constant. So finally I will be getting this equation as 1 by r dr within the limits of x and x plus a. Now the integration of this 1 by r dr will be equal to log r, so this will be equal to mu naught Ia upon 2 pi, the natural logarithm of r within the limits of x and x plus a. So this is equal to mu naught I a divided by 2 pi, and this will be equal to this. This is the natural logarithm, and this will be equal to log x plus a minus log x. So finally this equation can be written as, that is the magnetic flux linked with the square loop of side A. This will be equal to mu naught I a upon 2 pi mu naught I a upon 2 pi, and this will be equal to the natural logarithm x plus a divided by x, because we know that the log a upon b is equal to log a minus log b. So by using this equation, by this relation, or you can say the equation, I have written this this value as mu naught Ia upon 2 pi, the natural logarithm in bracket x plus a divided by x. So this is the magnetic flux which is linked with the this square loop of ABCD due to the this long current carrying wire. Now we have to find the mutual inductance. So the mutual inductance, as we have just studied, this is equal to phi, that is the magnetic flux linked with this square loop ABCD divided by the current which is flowing in this wire. So this is equal to mu naught I A upon 2 pi and log x plus a divided by a and divided by I. So this is I. So this I and I will get cancelled out, and finally the answer will be mu naught a upon 2 pi log x plus a divided by, sorry, this is x. So this is the answer, that is the mutual inductance between the wire and the loop will be equal to mu naught a divided by 2 pi into log of, this is the natural logarithm in bracket x plus a divided by x. So thank you very much for joining this session. In the next session, I will be now discussing another topic, that is Lenz's law. And so till then, have a nice day. Bye.